This is a bench test to prove that an oil leak below the surface of the ocean can be collected and piped to the surface in a self-sustained free flow. That is, the oil will flow by itself and will have enough pressure to rise above the surface of the water into a waiting tanker. The fluid dripping off the end of this hose is oil. The rising oil is powered by the difference in weight between the oil and water. We all know that oil floats on top of water. This occurs because a gallon of oil weighs between 7 and 7.5 pounds, and a gallon of water weighs about 8.5 pounds. The oil is freely flowing several inches higher than the water level, which is at the top of the open hose you see fastened to the wooden plank. In this case, the water column is 9 feet high. However, if this water column was 5,000 feet deep, the oil would be able to rise hundreds of feet above the surface and would have more than enough energy to push itself into a waiting tanker. An analogy of this device would be a fireplace chimney. The hot fire heats the air, which makes it lighter than the surrounding air and causes it to rise out of the chimney. The oil used in this test was vegetable oil, which weighs about 7.5 pounds per gallon. Crude oil may weigh less than 7 pounds per gallon and would therefore rise even faster and higher. I'll explain the test setup. At the base we have a large glass jar. Inside the glass jar is a collector in the shape of a cone. For the purposes of this test, it's just a simple household funnel. Below the collector is a thin hose, which is simulating the leaking oil source. Fastened to the lid of the glass jar is an outer hose. Water was poured into the top of this open outer hose, which filled the glass jar at the bottom and then filled the outer hose right to the top. The high column of water above the glass jar generates water pressure down in the glass and simulates water pressure at the ocean bottom. In this case, it generates 9 feet of head pressure at the bottom of the collector, or about 3.9 pounds per square inch. Inside the outer hose is a medium-sized hose representing the pipe from the top of the collector, also known as a funnel, to the surface of the water. We can call this hose the chimney. Also, oil is being pumped through a thin hose inside the outer hose from the reservoir at the top of the setup to simulate a leak below the collector. You may have noticed a fellow adjusting a valve at the top of the setup. He was just adjusting the flow rate of the simulated oil leak during the test to suit the height of the test apparatus and the diameter of the chimney. The actual flow rate at which leaking oil can be recovered depends on the leak depth and/or the diameter of the chimney. Keep in mind that the moment the oil contacts the water below the collector, it is at the same pressure as the water and it is not being forced upward by the pump. In fact, if you look closely, it is obvious that the oil is simply rising in the water and not being pushed up by the pump. The sole purpose of the pump in our bench test is to push oil to the bottom of the test apparatus to simulate an oil leak. If the oil leak had gas in it, the gas would simply rise with the oil in the chimney. Again, the oil flowing out of the chimney hose is doing so simply because of the difference in density between water and oil. So there you have it. Bench test proof that it should be possible to contain, collect, and control a submerged oil leak which in turn can be directed to a tanker at the surface. No need for a disastrous oil spill on the surface, and no need for huge oil plumes below the surface. Now, if hydrate or ice crystal formation is a problem, there is a simple solution. Electric immersion heaters similar to those in an old-style electric kettle could be placed below the collector. A cable from a generator on a surface vessel could supply electricity to any number of immersion heaters suspended below the collector. The amount of heat required to raise the temperature of the water, oil, and gas above the hydrate temperature would be easily controlled from the surface. Directly heating the water with electricity where it is actually needed is much more efficient and simpler than using hot water from a heat source 5,000 feet above. A pumped-in hot water setup from the surface would be more complicated than a simple electrical cable. First it has to be heated on a ship, then pumped through a pipe to finally get to the oil leak. The pipe would have to be insulated or there wouldn't be any heat left in the water. And finally, the hot water may push the oil around too much, reducing the amount that is collected and controlled. In other words, some oil may spill out of the collector and cause more environmental damage. Here's a sketch of how the system could be set up. Anchors would be placed around the leak source. The collector would be held in place by cables to the anchors. The chimney, which could be flexible, would be connected to the collector, and the top of the chimney would be connected to a flotation assembly located about 30 feet below the surface, or below the influence of waves. Another flexible hose would be connected to the chimney and carry the leaking oil and gas to a tanker. This patent-pending technology, together with the detailed patent documentation, was sent to BP Deepwater Horizon Crisis Team on May 5, 2010. This simple solution could be set up in standby mode at every drill site. If a leak were to occur, it could be brought under control within hours rather than weeks or months.